All right. So here's what I'd like to do. I want you guys to answer with a 1 or a 2. So put up your fist, stand up against the man, or in this room, I guess it's the woman. 1 or a 2 based on whether or not the examples I give you are either rotation or revolution. So, a ice skater spinning at the end of their long program.
Rotation.
There you go. There, we got it. All right, that's right. It's rotating. A revolving door. Oh, I see some 1s and some 2s. Oh, it's a misnomer. It's a revolving door, but what's it actually doing? It's rotating. I would like to start, by the way, an official campaign to change the name. But what about the people walking through the revolving door?
They revolve. They're not being pulled towards the center. They're just pushing around.
They revolve.
They're not being.
No, they're not. I mean, you're in charge of where you walk. It's not a gravitational pull. But they are revolving. That's true, but they're moving in a circle around an external axis.
It's not always gravitationally induced revolution.
Yes, you can decide when you want to take a turn. All right, how about, let's use another example. How about a car on an on-ramp to the highway?
What?
1 or 2?
The wheels of the car or the car itself?
The car, the whole car.
Like that. That's
Yeah, around us. So on the on-ramp, is that 1 or 2? Is it revolving or rotating? And that is correct. It's a number 2. It's revolving. So it's not like a strong gravitational pull in the center of the on-ramp. It's just friction, okay? So it doesn't have to be just gravity.
what you said it's center seeking. If there's nothing that it's seeking towards the center to, it can't go along.
All I'm asking you is revolution versus rotation. That's all. That's all. Just that. Just that. Stop arguing with me. All right. Yeah. How about the Earth every 24 hours? That's a number 1. Rotation. Every 24 hours, the Earth rotates. How about every 365 days? And that was a trick question because technically it does both, right? In 24 hours, it both rotates. I know. I knew what you were thinking. All right. The moon every 29 days.
What? There's not. What are you doing? Rotate
Yes, it does. And by the way, that was a trick question. Nice job, Andrew. It does both. It both rotates and revolves, and it's in a synchronous orbit, which is very typical. It is very typical that orbiting bodies, when they're captured by a central large gravitational pull, so like a star, a planet, or the sun, or a galaxy, or a black hole, when those objects kind of come into orbit, their rotation and their revolution match. So now I need 2 volunteers.
kind of like
1, 2, Stephen, Andrew, go to the back of the room for me.
So like relative cost relative to say the sun.
Yes. So the moon always appears, because it does have the same side toward us, yes. All right, so Stephen is the Earth, Andrew is the moon. Match your rotational and revolutional period. Oh, well done. Well done, sir. Nice footwork, too. All right, now I want you to imagine that Stephen is the sun and Andrew's the Earth. Do what it does. There we go. Okay, it gets more complicated, but yes. How many times does he have to spin in one circle?
365.
365 times. No, okay, I'm just kidding. Now, all right, Andrew, nice, well done. Now what I'd like you to do is put yourself in a synchronous orbit. Now he's still the Earth, okay? Imagine he's the Earth, Stephen is the sun. Beautiful, beautiful. Okay, stop right there. Stop. But look at Stephen. Look at the sun. Look, turn. There we go, beautiful. Imagine now you're living on the Earth on Andrew's nose. Besides it being a beautiful mountaintop peak, what's the climate going to be like? Stephen, you really have a hard job, don't you? What's the climate going to be like on Andrew's nose if we're in a synchronous orbit?
UV light would destroy the
It would be dang hot, wouldn't it? Why? Always facing the sun. So that would be a desert. It actually probably would be inhabitable, right? 24 hours a day of daylight. What if you were now living on the back of Andrew's head? Yeah. Darkness 24/7, right? Always dark and freezing cold. So where would the desirable real estate be?
Upon the right of Andrew.
His ears, agreed. Everyone wants prime real estate. The most expensive property on Andrew's head would be his ears. So, it's a dang good thing that we are unusual on this planet. Agreed? Because we are not in a synchronous orbit. Thank you, gentlemen. Come up here. You each get an extra credit point for your fabulous participation. Go ahead, Quentin. Well done. Stephen, I know that was rough for you. Good job.
So will the human race person like rotate it, couldn't it somehow like rotate with the same side always facing the sun?
It could, and that's actually more typical. When gravitational bodies are captured, they match. And that would suck for us because basically our planet would not be habitable if that was the case.
Then wouldn't it not rotate, because then this is part of the Earth rotating that way?
Yeah, but it's not that would not be rotating. We're talking about doing what Andrew did. So rotating one time for every time around.
No, it would be rotating space.
Yeah,
But at the same time, so space, that's not what we do. Wouldn't
that's correct. So the Earth, we do rotate. We rotate a whole bunch.
if you're just talking.
Do you need to get up and run around in circles?
Oh.
Okay. All right. Let's do a quick conversion now.
It would be the same effect, but a day would be 365 days long.
Right.
It would be really, really disturbing.
Okay. So now we're going to have a way to convert between angular and linear terms. I'm hoping that equation looks familiar. Theta equals S over R. S is arc length, and R is radius. Does that help? No? Radius. All right, let me do this. If we take a circle and take a radius and like pop it off the circle and then slap it down around the outer edge. So like from here to here. So do that. Lay it down.
So 2 pi r times theta over 360.
Yes. Yes, that is where we're going. So S equals R. So that's a radius length. The angle captured is 1 radian. That's the definition of a radian. So 1 radian. And a radian is about 57.3 degrees. 57.3 degrees. How many, and Wes already said this, how many of those 57.3 degree pi pieces will actually fit? 1, 2, 3, 4, 5, 6, and a little bit more. How many is that? Yeah, that's correct. So there are 2 pi radians in 360 degrees. That's the natural world. That's the way it works. When we determined this, when this is just defined as the number of radians that will fit in a circle. Okay? So this is going to be the basis for our translation between angular and linear stuff. Now, we have on our equation board distance, velocity, acceleration, and time quantities. So these are both distances. This is an angular distance. That's a linear distance. So now let's just divide both equations by time. And this part right here, distance over time, what's another way to say that? Speed or velocity, good. So the radius has to come along for the ride. And instead of theta, we're now going to call this omega.
Holy Jesus.
Oh, the irony for the next one. You'll get it when I get there. So theta equals S over R, omega equals V over R. That's radians per second and like meters per second. Okay? Then we're going to do the same thing one more time. Divide by time, and then wha-bam. And another way to say meters per second is acceleration. And then the angular symbol that we use is it's the Jesus fish. You get it? He said sweet Jesus, and now it's okay. That also has a non-religious name. That's a fish too. It's alpha. Yeah, alpha. So if I rewrite this without all the derivations, it becomes the following. And that's going to go up on the board. So there are your conversions between angular and linear. Okay? Conversions. So, every time, if you look on the board, you see all those linear kinematics equations. Every time you see distance, you could substitute theta. Every time you see velocity, you can substitute omega. Every time you see acceleration, you can substitute Jesus. You can substitute alpha. And every time you see time, well, what's time if you're spinning? It's just time, yeah, no difference. So here's what I'd like you to do. Yeah, that's true. If you go really fast, time does change. So here's our linear quantities. I want you to rewrite all of these. Okay, I want you to rewrite all four of those equations in angular terms. So all you're going to do is anytime you see S, I want you to substitute theta. Anytime you see velocity, I want you to substitute omega. Anytime you see t, just leave it as t. So just rewrite. It's like you're translating from like English to Spanish or English to Latin or linear to angular. Go. Dang it, Nick.
What acceleration would you use, alpha?
Yes. Thank you. Nice catch, Quentin. You get an extra credit point for
What?
catching that. Do not, you should be joyous in your classmates' success, Leslie.
Envious.
Well, I could do that on a test. I could, like, just write a gobbledygook word in linear terms and then have you translate it into angular.
what?
That'd be fun, that'd be fun, that'd be easy, right? You want that,
And that just be our.
the whole test, just translate like a whole paragraph.
Latin all over again.
Yeah, just put a whole bunch of stuff in one. That's it.
Yeah, except for you can't use Google Translate for that. Not that you do that with your foreign language homework.
I actually don't, because Google Translate, you remind.
Yeah, I know, it's like all the wrong order and stuff, right?
That guy with a hat down there, he was in our camp.
Greg?
Like a revolution.
Yes.
It doesn't have a radial, a radial velocity.
No, it's, you can still describe it in terms of its tangential velocity. You can, yes.
But would it change, like, the further one you get?
Yeah, if it's, that's correct. If it's an elliptical orbit, it will be constantly changing. So that, you have to use calculus to basically solve for elliptical orbits. Because it's non-constant. All right, let's see how you did. By the way, they're on, these equations are on the board and they will live there until end of January. So theta equals omega times t. Alpha equals omega final minus omega initial over t. Theta equals 1/2 alpha t squared plus omega initial t. And omega final squared equals 2 times alpha times theta plus omega initial squared. So hopefully that's what you have in your notes. It is a whole new language. So what we're going to be doing tonight is actually not new stuff. It's the same, it's using these kinematics equations, but in angular terms. So we're going to practice, notice on the homework, it says 7A through 7F. So it's basically one from each. If you go online and you check the answers, it's the highlighted ones. And just do, I think there's a couple that like for section, let's see, 7. I don't know, as I got further into this, I had more than one for 7, I don't know, D or E. Yeah, for 7E, I said 2 and 4. Just do the first one, whatever the first one is, and we'll practice a few of them right now. Did you have a question, Quentin? They're coming back. Don't worry. It's just, they're just